Okay, so on this particular page, I just want to point something out here. If there is an optional section, and again I say if with reservation, I would consider this to be kind of the optional thing. A lot of what we do in calculus, you're not going to use the in-depth identities that they showed you in trig. They do come up, and I've seen a lot of students who, the stronger they were on their trig identities, they got to the answer that much quicker. But the idea in calculus is not necessarily to verify or prove these things, but there is value in working through the identities. The identities themselves allow us to see things abstractly and sort of look for patterns within a pattern. That skill does come up in calculus. Okay, so kind of like graphing rational functions, I think is sort of the first practice one might have, and you do an analysis. This is probably the best practice in thinking creatively mathematically. There are more than one way to get to the answer, and there are a lot of good ways and a lot of bad ways to get to answers. Okay, so that said, the way I kind of mapped out this section is let's just see how good you are. Let's see what you remember, and then I'll post up a chart with all the identities in it. So take a minute and see if you remember what the reciprocal, quotient, Pythagorean, all the different identities that were out there. When you're ready, go ahead and press play again, and I'll put up a chart emphasizing all of these different identities. And again, this is another flashcard section that I would definitely have handy, because again, a lot of this you're not going to use, but it does come up on occasion. And it would be nice if you're that kid that raises their hand and go, oh, I remember this identity in trig. Anyway, so press stop, pause now, see how much this chart you can fill in, and then we'll come back and see how you did. Okay, so let's start with our reciprocal identities. Honestly, even though there's 6 of them listed, if you just know the main 3, that sine is related to cosecant, cosine is related to secant, and tangent's related to cotangent, then you should be fine. We got our quotient identities, which are those top 2, with tangent equals sine over cosine and cotangent equals cosine over sine. So hopefully that's what you got. Pythagorean identities, you will use this. Definitely sine squared plus cosine squared equals 1. That comes up a lot. And I've seen tangent, Pythagorean identities I would know. Those are definitely big ones that come up a lot. Even and odd, you might have called those cofunction identities. I didn't even put those in my chart. I won't say they won't come up, but I didn't emphasize it. Double angles. Double angles are an example of something that will save you time. If you can recognize it, then that'll make solving the equation that much easier for you. Let's see, I need half angles. Come all the way back up here. Come here. Okay, half angles are right up at the top here. And those are good. You will definitely in Cal 2, there'll be a process that comes up. So you will use half angles when that comes up. Sum and difference are, again, those are another time saver. If you remember those, then that'll help you get the question solved that much quicker. And then law of sines and cosines. I'm going to go to my last page of formulas here. Okay, those are those 2 formulas. There's more formulas, and you probably go, I've never seen those before. Well, law of sines and cosines typically gets the job done, so we don't have to go to law of tangents or this other special case. But I have seen some calculus questions come up where law of sines and law of cosines came up, and if you didn't know it, then you weren't able to work it out. Okay, so that said, the rest of this we're going to practice some identities. And again, let me just kind of point out, the intention here is to practice abstract creative thinking. So it's can you connect the dots to show that one side happens to equal another. And I didn't pick incredibly rigorous ones. I picked ones that were pretty straightforward, just to kind of give you a warm fuzzy and let you understand that, yeah, I do have a good handle on this. Okay. Um, let's start with number one here, cosecant times cosine. Can I get that to show it equals cotangent? Well, how else can I write cosecant? Cosecant is really 1 over sine times cosine. Okay. Well, I can multiply that and put it in one fraction, so that's cosine theta over sine theta, and that in fact does equal cotangent theta. So I got cotangent theta. I got it to work. Okay. Um, Typically, when you're doing identities, you only want to manipulate one side of the equal sign, and the general rule is you want to manipulate the more complicated looking of the two. Okay, number two, cotangent theta over cosecant theta. Can I get that to reduce down to cosine? Well, one approach would be to convert everything to sines and cosines and see what shakes out of that tree. So if I go cotangent, would be cosine theta over sine theta, and cosecant theta is 1 over sine theta. I notice that they both have the same denominator, and so it does in fact reduce down to cosine. So I get cosine equals cosine. So I was able to verify that. Okay, so in number three, again, one great approach is to try to convert everything to sines and cosines and see what happens. And again, I only want to manipulate one side, and typically it's the more complicated looking. So cotangent plus tangent, I think, is a lot more complicated than just secant, cosecant. So cotangent is cosine theta over sine theta plus sine theta over cosine theta. Okay. I want to do a common denominator. Common denominator would be sine theta cosine theta. Okay. Well, what was the first fraction missing of that common denominator? Well, it was missing a cosine. So I take cosine times cosine, so I get cosine squared theta plus, and here I take, what was the second fraction missing? The second fraction was missing sine, so sine times sine is sine squared theta. And hopefully we'll recognize this. Cosine squared plus sine squared, that's a Pythagorean identity, and that we can replace with 1. So I end up with 1 over sine theta cosine theta. Okay. Well, 1 over sine and 1 over cosine, that's just another way to write secant and cosecant. So I get secant theta cosecant theta. I think I'm getting excited here. Secant theta times cosecant theta. And that in fact equals the original. So yay, I got it done. Okay, number four is a great illustration of the sum and difference of sines, specifically sum of sine. So if I expand that out using the sum of sine formula, I get sine of pi halves times cosine theta plus cosine of pi halves times sine of theta. Okay, well, sine of pi halves, that's just 1 times cosine theta, and cosine of pi halves, that's 0 times sine theta. Well, what happens? Well, the 0 kills that side, and I'm left just with cosine theta. All right, so we were able to verify that. Okay, so these last two got a little more rigor to them. It kind of makes us feel like we know what we're doing, especially if we try something hard and get it right. So I'm going to, first thought looking at number 5 is, Both fractions kind of look about the same level of difficulty. I'm going to challenge you and say that secant theta is a little more complicated than cosine theta. But as a matter of fact, that's what I'm going to do first. Is I'm going to convert secant to 1 over cosine. So the left side becomes 1 plus 1 over cosine theta over 1 minus 1 over cosine theta. Okay, and then I'm going to make a common denominator. Okay, the numerator's got a denominator of cosine, and this 1 here was missing the common, so 1 times cosine theta plus the initial 1 that was there, and the denominator is going to have the same concern. So cosine theta over, and that 1 was also missing cosine, so 1 times cosine theta minus 1. Okay, and what do I notice? Well, I happen to notice they're both being divided by cosine, so that's going to leave me with cosine theta plus 1 over cosine theta minus 1, which is what I was trying to show. So yay, got that one. Okay, and then lastly, number 6 here. So I think clearly the left side is the more complicated one. So 2 minus, we're going to convert that to sines and cosines. So 2 minus sine theta over cosine theta over 2 over cosecant is 1 over sine, so that converts to 2 over sine theta, minus secant, which is 1 over cosine theta. And then I'm going to common denominator all of this. So in the numerator, I have a cosine theta as my common denominator. And then the 2 happens to be missing the cosine. So it's 2 cosine theta minus sine theta. Okay. And then in the denominator, let me make that so we can see it. Denominator, the common denominator would be sine theta, cosine theta. Okay. Well, what's this first fraction missing? This first fraction that says 2 over sine, it's missing the cosine. So that becomes 2 cosine theta minus, in the second fraction, it's missing the sine, so 1 times sine gives us sine theta. And then hopefully you can kind of see what's going to happen next here. I've got, and I'll kind of write this out as a complex fraction, so, or flipped reciprocal. So I've got 2 cosine theta minus sine theta over cosine theta. That's the numerator. And in the denominator, I have sine theta cosine theta over 2 minus cosine theta sine theta. Okay, well, that's pretty much a dividing barrel of joy. Everything divides out except for the sine theta, which is what I was trying to show, was that initially it was simplifies down to sine theta. So, nice little phrase that I like to throw out there, QED, which stands for I am done. I set out to prove what I was trying to prove, so there we go, QED, and we got this.